that at time t, the location of the particle was x of t and y of t. Okay, x of t and y of t. In other words, this is the location of the particle at instant, what do you call, t. Are you getting the point? And so in other words, for each instant there is an address. Okay, to each instant there is an address actually. So if x of t and y of t are, say, defined by some formula, for example, x of t is t and say y of t is, say, t square, okay, then these are called the parametric equations. These are called the parametric equations actually. These are called the parametric equations. So what is the meaning of parametric equation? You have this time axis roughly, and to each instant you have a position associated with it. So if you combine all positions, you're gonna get curve. In other words, if you trace out, if you graph x and y for all times t, you're gonna get this curve actually. Okay, you're gonna get this curve. So now what we are interested in now? I am interested in computing the length of this curve, L-E-N-T-H, of this curve. And if I will compute the length of this curve, what is going to tell us? It is going to tell us that how much distance this particle has covered in this time. So in this time, how much distance this particle had covered actually. Okay? So this is what I would like to do. And we're going to show that again our notion of what do you call, integral, okay, is going to help us even to compute the length of a curve. Okay? If you have been given its parametric equations. Okay? Where t is like the parameter on which x and y depends. So length of the curve. Imagine I give you this curve and I say compute its length. How are you going to compute it? What would be the tricks to compute it? You can say, okay, if this curve is like a rope, okay, then I can stretch that rope and then, you know, measure this, for example, this rope, okay, or this length by some suitable, maybe, you know, measuring tape or some scale actually. So you can do it. So treat this as a rope, stretch it, okay, straight it and measure it through, you know, some measuring tape or some scale actually. But imagine this is not like a rope actually. It's something solid. You can't stretch it. You can't change its shape actually. Okay? And someone gives you, for example, one scale. Okay? So it's like, I know that this is, for example, 2 centimeter. Using this, can you compute the area of, for example, the length of this curve? So what you're going to do naturally? You're going to say, okay, let's put this curve here. So this is 2 centimeter. So it's like, you know, draw a line. Draw a line. This is 2 centimeter. Then you're going to do what? Again, put it here. So approximately this is also 2 centimeter because this is the only available scale to you. Okay? You're going to say this is 2 centimeter. And you're going to say, okay, then again put it here. So you have 2 centimeter. You're going to say, okay, again put it here. So in other words, what you're going to do, you can approximate this by these straight distances, okay? By these straight distances. So if I have some measure, then I can do what? I can compute these straight distances and I can get what do you call the length of the curve. But the trouble by doing it is going to be what? The trouble is going to be that there is going to be a lot of error. Okay, so there is a lot of error actually. Okay, it's not the actual length. So this yellow line is not the actual length of the, this piece. Yellow line is not an actual length of this piece. So what you can do actually? So here is another thing that you can do. Okay, here is another thing that you can do. So rather than taking a big piece and trying to approximate through the big piece, let's take, for example, a smaller piece actually. Okay, let's take a smaller piece and try to approximate it. So put this piece here, 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 here. So what are you gonna get? So approximate it through small lines and keep on making these lines smaller and smaller and smaller actually. Okay? Smaller and smaller. So as you make these lines smaller and smaller, you will see that you're going to get a better and better approximation. You're going to get better and better approximation. So if you want to compute this entire area, compute the area of this segment, the length of this segment plus length of this segment plus length of this segment, length of this segment, length of this segment, plus length of this segment and length of this segment. So add the lengths, okay, of these segments, these tiny segments, and you can get an approximation for this area. You can get an approximation for this length. Okay. Now to how to compute this. So imagine all this is in XY axis. This is an XY axis. And imagine you take, for example, this ith line. Okay, this ith line that approximates some part of this curve. So imagine that this ith line has two coordinates. Okay, so it has two coordinates. So the one coordinate is this. I use more. One coordinate is this and other coordinate is this. And say the coordinate of this are, say, I don't know, xi, yi, and say the coordinates of this are, say, xi plus 1 and yi plus 1 actually. Okay, yi plus 1. And imagine that all of these lines have equal length actually. So you are always approximating the curve by equal length, no matter how small it is, but they all are equal actually. Okay. Then what would be the change in the coordinate x is x? So for example, if I call delta x as xi plus 1 minus xi, and delta y as, say, yi plus 1 minus yi, and say this point is pi and this point is pi plus 1. Okay, this point is pi and this point is pi plus 1, and the change in the coordinate axis is from xi to xi plus 1 is delta x, and y to y plus 1 is delta y, and this is same for all segment actually. So in other words, you take these 2 points and compute the difference of x coordinates is going to be always delta x, and compute the difference of y coordinates is going to be always delta y. In other words, all these segments have equal length actually. Okay. The question is, what would be the length of this segment pi plus 1? Okay, what would be the length of this? So in order to compute the length of any segment, you need to apply the distance formula. So the distance formula is going to be, take the difference of the coordinates xi plus 1 minus xi. In other words, let's call it delta x square, and yi plus 1 minus yi, and let's call it delta y square. So this is going to be the distance between pi plus pi plus 1 actually. Okay, this is what that you're going to get. And if you sum all these segments, so imagine these segments are n segments. So if you sum the lengths of all these segments from I equal to 1 to n, okay, you're going to get the length, you're going to get an approximation for the length of this curve. So you're going to get an approximation for the length of this curve actually. Okay? So it's like summing up from I equal to 1 to n, like this quantity delta x square plus delta y square actually. Okay? Can I turn this into an integral? The answer is yes. If this curve is like a parametric curve that is defined by x, some formula in the terms of t and some formula in the terms of t. So I can do this, that okay, let's divide and multiply these both quantities by delta t square. Okay? Divide and multiply the both quantities by delta t square. Okay? So this sum is going to be I equal to 1 to n. Okay? So you're going to have delta x by delta t square plus delta y by delta t square, and this square root of delta t square will become delta t. Okay? So it's going to come out of, what do you call, the integral is going to be delta t. So if you want to compute the actual length of the curve, what you need to do, you need to increase the number of line segments actually. You need to take this limit n to infinity. So when you're going to take this limit n to infinity, okay, this sum will become integral. This delta x by delta t, so this will become, what do you call, dx by dt plus dy by dt square, and this delta t will become dt. And integrating it from where to where? Whatever is the domain of definition actually. Okay? So if t varies between say point A and B, then this integral is going to be from A to B. So this is the formula really to compute the length of the line segment curve. Okay? So it's a pretty nice, neat and clean formula. It's not difficult. So if you have been given, for example, x and y in the terms of t, calculate these derivative and compute this integral, you're going to get the length of the curve. So let me do one example. Okay? Let me do one example. For example, I have a curve x equal to t square, y equal to t cube, okay, and I need to compute this integral between, I need to compute the length of the curve, which is defined by this formula x equal to t square and y equal to t cube, between these 2 points from 1, 1 and 4, 8 actually. Okay? 4, 8. Now, here is the thing. So, how does this curve is going to look like? We can easily paint this color actually, that this curve is going to look like something like this actually. Okay? This curve is going to look like something like this. So we don't have to compute the curve of entire segment, but we need to compute the curve between 1, 1. So 1, 1 is maybe, this is 1, 1. Okay, and 4, 8. This is 4, 8 actually. Now here's the thing. For what value of t, these two formulas will give you 1, 1. In other words, x will become 1 and y will become 1. So you can guess it that if you take t equal to 1, then x will become 1 and y equal to 1. So in other words, I can represent this point by t equal to 1. Okay? So in other words, this point is, x evaluated at 1 and y evaluated at 1. So this is going to be t equal to 1. Can you guess that when you are going to, for what value of the t you're going to get this point 4, 8? So you can guess correctly that, okay, substitute t equal to 2. So this t square is going to become 4 and t cube is going to become 8 actually. Okay, so t equal to 1 to t equal to 2. Okay, so this t equal to 1 is like the point 1, 1 and t equal to 2 is like the point 2, 2 actually. So what I have to do, I have to compute this integral. So in order to compute this integral, I need to compute what? I need to compute dx by dt. So what would be dx by dt? So it's going to be 2t. What would be dy by dt? Okay. What would be dy by dt? So it's going to be 3t square. So we have to compute the area of this segment. Okay, this segment. So the length of this segment. Okay, so forgive me, I'm again and again calling it area. So this is going to be an integral. So dx by dt is 2t square. Dy by dt is 3t square and dt. Where t varies from this point to this point. In other words, t varies from t equal to 1 to t equal to 2. So 1 to 2. So just solve this integral and you're gonna get your result. So how can we solve this integral? It's not difficult. 1 to 2, this is going to be 4t square, 9t power 4 and dt. Okay? So if you pull out t, from 1 to 2, square root of, so the t square is like, common in both actually. So you can pull this t out. So it's going to be, 4 plus 9, okay, 4 plus 9 t square times t square and dt. Okay. So you can get rid of this square root and square here. So now you have this integral that you have to compute. How you can compute this integral? You can make a substitution. Why? Because you have a quadratic term inside the square root and you have a linear term outside. So it's like its derivative is present outside actually. So if you make a substitution, u equal to 4 plus 9t square, then du by dt will become 18t. Okay, and hence du will become 18t dt. So you have a t here, but to turn it into du, you have to multiply it by 18. So I need to multiply this by 18, and as a result I need to multiply this by 18 here. So once you're going to have this, what you can do, by the way, you can also change, you need to also change the limits actually, these 1 and 2. So if t is 1, what will become u? So the u will become 4 plus 9, so in other words it will become 13, okay, for t equal to 1. How about t equal to 2? U will become 4 plus 9 multiplied by 4, in other words 36, so it's going to be 40 actually. So when you're going to simplify this, you're going to get 1 over the square root of 18, 1 will become 13, 2 will become 40, square root of 4 plus 9t square will become square root of u, and 18t dt will become du. So now you can easily calculate this integral, and once you calculate this integral, you're gonna get something interesting, and you will have this number. I'm writing it directly, so it's gonna be 1 over square root of 18, okay, 80 square root of 10 minus 13 square root of 13. Okay, this is what that you have to solve for yourself. Okay, we saw an interesting formula for computing the derivative of x. By the way, how about if I have been given a curve that is not a parametric curve actually? Okay, I have been given a curve that is not a parametric curve. So in other words, imagine I have been given, for example, a curve like this whose function is known to me simply y equal to f of x, and this function is defined on an interval a to b. Then how to compute the integral actually? Okay, then how to compute the integral? The answer is that you can deduce it from the same formula. So what is the formula? A to b square root of dx by dt square plus dy by dt square and dt. Okay, so I can do this. So for example, if I take common dx by dt square from these two terms, so here you're going to get 1, and here you're going to get dy by dt square divided by dx by dt square and dt. Okay, this is what that you're going to get. If you simplify this a little bit more, okay, this thing in the interval is going to be, square root is going to be dy by dt square and dx by dt square. So this dt square will cancel, and you're going to get dy by dx square. This dx by dt is going to go out, so it's going to have dx by dt times dt. So this dt will cancel out, and the final formula that you're going to get in order to compute the area of, okay, the length of the curve is going to be an integral from a to b square root of 1 plus dy over dx square times dx. So simply compute this integral, you're going to get the area of the curve actually. So if you have been given a parametric set of equations, just substitute, just calculate the the length of the segment through this formula, and if you have been given a function y equal to f of x, just use this formula to calculate the length of the curve actually. Okay. Let's do one example. Say you have been given y equal to, I don't know, say y equal to x square. Okay, you have been given curve y equal to x square. Maybe y equal to square root of x. Okay. Let's take, for example, a simple function. So imagine you have been given a function y equal to f of x, which is, say, a straight line. Okay, I don't know. So it's like say y equal to x plus 1 or f of x equal to x plus 1. And you have to compute this area, for example, for x between 0 to 2 on the interval 0 to 2. So if you want to compute the length of the what do you call the area, not the area but the length of this curved segment from 0 to 2, okay, this is going to be like finding the distance between these 2 points. Okay, so you should get the same distance because this is a straight line. Okay, so you should get what do you call the same. So through this formula you should get the same length as you get, for example, through computing the distance between these 2 points. Where this point is what? This point is when you substitute x equal to 0, so it's going to be 0, 1, and this is this point when you're going to substitute say x equal to 2, so it's 2, 3, for example. Okay, so the distance between these 2 points by directly computing it is going to be the square root of 2 minus 1 square plus 2 minus 0 square plus 3 minus 1 square. So hence it's going to be 4 plus 4, so square root of 8. So let's see that through this formula, do you get the same actually? Do you get the same? So in order to compute the length of this curved segment, okay, through this formula you need dy by dx. So if your y is this, what would be dy over dx? So it is going to be 1. So if you compute, for example, L from 0 to 2, and you have square root of 1 plus 1, and what do you call dx actually, okay, and you compute this integral. So this is like square root of 2. You can pull it out of integral, and what is going to remain is inside is 0 to 2 dx. So hence the output that you're going to get, this L that you're going to get is really square root of 2x from 0 to 2. And if you substitute this, you're going to get square root of 2 multiplied by 2 minus 0. So you got 2 square root of 2, but 2 square root of 2 is really square root of 8 actually. Because you can write square root of 8 as 4 multiplied by 2, so hence you get 2 square root of 2. So you see that this formula kind of gave you a correct, what do you call, distance between the length of the curved segment actually. So if you have been given y as a function of x, just substitute values in this formula and you're going to get, just compute the derivative of y with respect to dx and substitute it into the formula, compute the integral, you're going to get the length of the curved segment. And if you have been given parametric equations, compute the derivative of x with respect to t, with respect to y with respect to t, substitute into the formula, you're going to get the length of the curved segment, anything that you like actually. So this is another interesting application of the integral actually. Let's talk about another little application of integral. So far we have seen 3 little applications of what do you say, integrals, okay, computing areas, computing volumes, computing the length of the curves, okay, and computing next is computing the average value of a function, okay, computing the average value of a function. Next is average value of So imagine you have been given some function, some y equal to f of x. You know, you can have anything. So you can have, for example, okay, a function y equal to or t equal to temperature at time t. Okay, temperature at time t. Or you can have, say, a function that represents v equal to velocity